The last problem we solve in this lecture is our old friend, the cable reliability problem, the 4-variable version of that, which we called example D1. So let's take a few seconds to recap this problem statement, and then we will solve this using Monte Carlo simulations. We have already solved this with FORM and SORM. Okay, so we have 4 random variables, x1, x2, x3, x4, out of which x1 and x2 are each independent of the other 3, and x3 and x4 are dependent on each other. So our limit state function looks like x1, x2 minus x3 minus x4, and in Monte Carlo simulations we have to generate these x1, x2, x3, x4 repeatedly. So for the first two, for x1 and x2, it's trivial. All we would need is to use the inversion method. X1 is the yield strength, Weibull, x2 is the area, normal. So we have the ability to generate them from the from standard uniform deviates by the inversion method. So that's straightforward. We already did this in the previous example involving the safe stopping distance. But for the correlated ones, we have to make sure that we ensure that the dependent structure is maintained. So x3 and x4 are dependent on each other, but they're independent of x1 and x2. So let R be the correlation matrix of x3, x4. That's all we know about their dependent structure. We don't know the joint distribution. So we have the correlation matrix, the 2 by 2 matrix, and we do a Cholesky factor, the lower Cholesky factor C, such that C transpose is equal to R. And then we generate independent standard normals, Z3 and Z4, and then we combine them linearly to obtain dependent standard normals, Y3 and Y4, with the help of C. So Y3, Y4 are linear combinations of Z3, Z4. And just to make sure that this way we get the mean of Y3, Y4 as 0, and the V of Y3, Y4 is R. And then we do an inversion of Y3 to X3 and Y4 to X4. This way we ensure dependence between X3 and X4. However, because of the nonlinear transformation between the X's and Y's, we do not end up with the same R that we started with. We have discussed this before. If it's very important to ensure the exact value of rho between X3 and X4, we should start with different values that we did at the top while finding the Cholesky factor. But even without that, the error is very slight in most cases. So now we are ready to present the Matlab code and then the solution. So we start with defining the basic variable statistics. We do it for Q, then we do it for A, we do it for D, and then we bring in the correlation structure between Q and D. So we define the 2 by 2 correlation matrix, and then take the Cholesky factor. And the last command in that line that you see is to make sure that it's the lower Cholesky factor. Then we obtain the statistics of y. So because y is Weibull, we go through that step. We have shown those before to get the shape and scale factors of the Weibull distribution. Then we are ready to start the loop. We have 1 million trials once again here. We are going to change that and show how the results keep getting better. We initialize the count, we start the for loop, and then we generate the random variables one by one. We first generate y from the command rand, which gives us the standard uniform deviate, and we invert that to get the Weibull y. We use the rand n command to generate the standard normal deviate, and then transform that to the normal a, and then for q and d we generate two standard normals, independent standard normals, z1 and z2, and then we linearly combine them to get y using the lower Cholesky factor. And then once we have y1 and y2, we individually invert them to get q and d. So q comes from y1 and d comes from y2 using the full distribution transformation. And now we are ready to check for failure. So our limit state is y a minus q minus d. So if failure happens, then we increment the failure count by 1. And that brings us to the end of the for loop, and we can output the estimated failure probability and the COV of that estimate. We have run this for 4 values of an MCT. The first one is just 1000 estimates, and that gives about 3.9% failure probability, but the COV is a bit too large, about 16%. So let's increase the number of samples. The next one is 10,000, still about 3.8%. The COV comes down to 5%. So we could stop there, but let's see how the improvement goes on. So 10 to the power 5 samples gives us about 3.9% and 1.6% COV. And then if we do 1 million simulations, it's still about 3.8% and it's 0.5% of error. So we can stop now. We could have stopped much earlier. And this result of 3.8% we actually used when we were comparing the accuracy of FORM and SORM.